This is CS402 on Monday, June 16th, 2014.
Let's get started. Warm-up 2 is due this Thursday. And again, I strongly encourage you to work with your potential kernel partner. There's a deadline for team forming for the kernel assignment. The deadline is this Saturday. You should check the website. So make sure you have, a group together. And I guess starting this week, if you have a group, you should send me, email to get it approved. The procedure is that every one of your group member have to send me an email and to tell me that this is your group because you can't say that person is on my group. Okay, everybody has to tell the same thing to me. That's the only way I can be sure that people are included because they want to be included. Okay, so please follow the procedure. Otherwise, it doesn't really count. All right, and make sure you don't copy any code, from previous years. And a reminder that the grading guideline is the only way we will grade, and we can only grade on nunkey.usc.edu. So if code works on your laptop, well, that doesn't really count for anything. It has to work on the grading account. And also the other thing is that there's a procedure called verify your submission. Make sure you do that when you submit something, so that to verify that you haven't really forget to submit any files. Okay, and if you follow that procedure, you will know that we don't really copy your my 402 list and stuff like that from the warm-up 1 directory anymore. So you should include those kind of stuff, in your .c and .h file in your submission. One thing I discovered last week is that the Monday office hour, there's somebody meeting in PHE 333, and it's going to take too long to resolve the conflict. And their meeting is supposed to only go till like 12:30. So starting from this week, if there's a conflict, at 12:20, if somebody's in the meeting room, so I will be in the lobby of PHE. So just that's where you get in. I'll be just sitting there until it's 12:30, and then I will go upstairs. Okay, and the lobby has chairs and stuff like that, so we can certainly I can answer questions there. All right. Oh, by the way, I'm surprised that nobody sent me email to say, hey, where's the kernel spec? Because I thought people, finished with the warm-up 1, they want to get a head start. So I just posted the kernel spec. Okay, so if you go to projects now, this link is alive now. If you click on this, okay, so read the spec. So one thing that you're required to read in order to understand what you're implementing is this documentation for Unix. Okay, over here it says complete documentation. So there's a source code you need to download, and then there's documentation. The documentation is 76 pages long. Okay, so it's a lot of reading. But of course, I mean, that's for the entire semester. So you should read the beginning part and the first programming assignment to get you started. So what I'm going to do, I actually have a lecture sort of on the OS project assignment. So if you go to the lecture slide, over here, there's one lecture slide called kernel assignments. Okay, so I will give you a brief introduction of what's required and stuff like that. What are the important things to get points for the kernel assignment? And my plan is to cover this in an extra lecture. Okay, so this Wednesday after office hour, I'm going to have another extra, pre-tape of the lecture. And the reason I'm doing that is because, we're losing the last lecture for final exam, so we don't have enough time. So I'm sort of making it up with the early lecture. Okay, so what I'm going to do is that in that lecture, of course you don't have to attend. I'm going to cover the kernel assignment. Also, I'm going to cover this part right here in chapter 3. There's something called dynamic storage allocation. I said we'll cover in extra lecture. Okay, so that's my plan for this Wednesday afternoon. And also the last part, booting, will also be covered in extra lecture. Okay, so the extra lecture I will cover these 3 things. Okay, so today's plan is to, last time we sort of briefly started static linking. So we'll definitely finish that, and then we'll start talking about what the operating system look like. Okay, and then, I guess, later, maybe Wednesday, hopefully we'll get into, how to implement threads in the kernel. But, the stuff in chapter 5, they are more talking about design issues. The really way to learn about how the threads is implemented is to, implement your kernel assignment. Because in the kernel assignment number 1, you have to implement threads. Okay, you have to implement kernel threads. And you're going to read the documentation sort of to find out what is it. It's kind of a weird thing. And the way the kernel is organized, it's a little bit not exactly what you have expected, but hopefully what we have covered so far, give it an idea what a thread looks like. Okay, and then you have to go implement it in the kernel. All right. So let's go to static linking. So these are important topic. I guess you don't really completely need this until kernel 3, because kernel 3, you have to take a user program and you need to run it. So you're the kernel. Somebody give you a user program and say run it, right? And so you have to prepare the address space, implement fork, and all that kind of good stuff, and I guess implement part of exec to execute that user level program. Okay, so you sort of need to have an understanding what a user program look like. Okay, so this is what this lecture is about: linking and loading. Now, hopefully that will give you a better picture of what it is, what is a user program. All right? Okay, so last time we talked about, I guess we talk about, relocation, right? So the idea here is that there are programs that can execute anywhere. If a program doesn't use global variable, then every variable that it uses are in the stack. So these kind of program doesn't really, it can be put anywhere and it should work. Okay. What about a program like this? You have global variables now, right? This guy has these things. Okay, so x, it says x is equal to 6, and then ax is a pointer that has the address of x. Okay, and then you have main program right here. The main program is going to call the subfunction. Okay, so these functions, they can be placed, well, the question is where can they be placed? Functions should be able to place anywhere in memory. But what happens is that when you have code like this, okay, how does it know where are the memory locations for x and y? Okay, in this case, x and ax. Okay, so I guess, let me go back a few slides. Oh, actually, we haven't really talked about that yet. All right. So, the idea over here is that, these memory addresses, we don't really know what they are at compile time. Later on, we sort of need to figure out what are the memory addresses for x and ax, okay? Because as we have seen the assembly code before, when you need to address a variable, you sort of need the address of that variable, okay? The stack variables or the automatic variables are easy. They are accessed relative to EBP, right? So the local variables and the function arguments, you access them relative to EBP, so you don't have to know where they are. Okay, all you need is the stack point, EBP pointer. You have a stack frame, right? So this is the stack frame, okay, and you have EBP pointing to it, okay, and this guy can access all the function arguments and local variable, right? So this stack frame can be located anywhere in memory, and it's all going to work as long as EBP point to the right place, right? And where does EBP point to? EBP point to this linked list of EBP pointers, right? Remember that? Okay, and this is the top stack frame because ESP is pointing right here. All right, so what about global variable, right? So that, over here, the address space, you have the text segment, you have data or code segment, and then you have data segments over here. We have X, we have AX. Okay, so in order for your program to execute code to access these memory locations, you need the absolute address in your address space. Go from 0 to 0x. You need the absolute address of these variables. Okay, so how do the program figure out what these addresses are? All right. So the idea over here is that at compile time, you don't really know what the addresses of these memory locations are. Okay. So these addresses can be moved around in memory. Okay, and that process is called relocation. Okay. Over here, so these programs that are compiled in a way, I guess when I ask you to do separate compilation, right? You say GCC minus C, something dot C, F dot C, it will produce F dot O. Okay? These F dot O are called modules, okay? And the modules are relocatable. That means that you can move around these kind of stuff anywhere in memory. Okay? And some of these modules actually contain memory addresses, right? If you have a .c file, over here you can say static int x is equal to 5 or something like that. Okay? So this x variable lives inside this module, okay, and it has an address, okay, and that address can be moved around, okay. So later on, when you have other code try to access memory location x, you need to know the absolute address for x, okay. So that memory address gets resolved a little later, okay. So at compile time, you don't really need to know the address of these things. So what you do is that you generate code where code have holes in them to say that, hey, I don't know what the value of x is, but it's to be filled in later on when I know exactly where that memory location is. Okay, so that's the job of the linker. Okay, so over here, linker, right? So remember that when we do separate compilation, we go GCC minus C something, GCC minus C something, and then finally we say, oh, camera operator, back on. The last step is GCC minus O, warm up 1, and then a bunch of .o files, and then you sort of link everything together. Right, so the first step, this is compile, and I call this guy the link step. Okay, so link over here is that you're invoking the linker. So the last step, GCC actually will invoke the linker. The name of the linker in Unix is called LD. Okay, there's a program called LD that get invoked, and the linker's job, it has two main functions. One is to perform all the relocations. Okay, for every module that it sees, it will determine every function, every global variable, what is the actual address for these things. Okay, every function also needs an address, right? If you have a function that you call, well, it has a memory address where the function sits, and the function sits in the code segment, right, or the text segment. Okay, and the data, those things sits in BSS or the data segment. Okay, so the linker's job is to perform relocation, give every variable a memory address. Okay, and then and then make sure that if you have a place to access X, now that piece of code is going to say access memory location, 1, 2, 3, 4. Okay, it's going to have an actual, numeric address for variable X. All right, and again, that's only for data segments and BSS segment. Right, things are in the stack, then they have a different way to access them. All right, and then the second job for the linker is to perform symbol resolution. Okay, so you can compile your code and you find out that, oh, this code is going to call, write. Okay, write is a system call. The system call is not implemented in your code. So it needs to go find out where is the code for system, for write, pull that code into the executable and put it into the text segment so that when you call write, it has a memory address, okay, and then it can call that function. Okay, so for any of the unresolved symbol, anybody see the compiler complaining unresolved symbol so far? When you compile warm up 2, you've probably seen it, right? Okay, so that's really not the compiler that's complaining, that's the linker that's complaining. It's trying to resolve some symbols, and you forgot to tell it something. You forgot to do minus LRT, you forgot to do minus LP thread or something like that. Then it says, I don't know where this function is, I give up. Okay, so you have to tell it where it is. After you tell it where it is, then it can resolve all these symbols. It will copy those code into the executable and give a new address for these things. Okay, when they try to copy the code, for p threads or for nanosleep or whatever, those kind of functions might also come with global variables. Okay, so you also need to copy the global variables into your data segment. So everything in those modules that are compiled in library somewhere, you have to pull them in and then pull it into your executable. Okay, because in the end, your executable needs to be a piece of self-consistent code that's ready to execute. You're ready to hand that piece of code to the operating system and say, go ahead and execute it. All right, so we're going to look at a little more detail now, look at what goes into the .o files so that, these kind of operations become possible. All right, so that's linker. Another thing is called loader. So over here, I guess I have a note here. I don't know if you see that before. Okay, the textbook is wrong. Okay, the textbook for some reason called this guy the loader. That's incorrect. Okay, and later on you're going to find out that the textbook actually has a few errors. I guess I have to talk more about some of the other stuff. All right, the loaders is the one that loads program into memory. Okay, so the loader is the one when you call execl, right? When you call execl, you say execute this program. Okay, so that program needs to be taken from disk and then loaded into memory because you can't really execute something until they're in memory. Okay, so the loader takes the data from disk, not the data, the entire file from disk, and then create the address space and put all the stuff in the address space. Okay, so that's what the loader do, right? It's a, but these days there are some loader that also perform additional relocation. So they're called relocating loader. I guess maybe that's why the textbook got it, got it wrong, because these days the loader also can perform linking. Okay, but to be more specific, as far as exam and stuff is concerned, the linker is the one that does relocation and symbol resolution, and the loader is the one that finishes up execl. All right. Okay, so we're gonna do separate compilation, in a slightly different way. So over here, we're gonna separate the previous code out into main.c and subr.c. Okay, in main.c, we're gonna have the main function. In the subr.c, we'll have the subr function. Okay, but on purpose, we're going to declare x to be in subr. Okay, and over here, the main program, we're going to have this, a keyword over here says extern. Right, you're familiar with extern now. Right, over here, this function says, I don't know where x is. X is going to be external to this module. Okay, and that's okay because later on, the linker will figure it out. Okay, so you can actually compile over here. So when this guy ax over here, reference the the unresolved symbol x, what it will do is that it will create a hole in the code that it compiles and say that, hey, later on the linker better fix it. Okay, so this guy could compile into main.o, and this guy could compile into subr.o. Okay, so inside main.o, if you look at main.o, you're going to see holes in them. All right, the holes are, I don't know where this guy is, and also I don't know where subr is. All right, because at this point it says subr is a function, right? It generates codes over here. Remember, what does the code look like for subr? Okay, so go back to the beginning of chapter 3. We saw the assembly code, right? This guy the code get changed into or get compiled into pushing the argument into the stack, creating the stack frame for subr, right? And then finally there's a machine instruction that says call subr. Right? Okay, so can I compile this code? Yeah, no problem. I don't have to know where subr is. Okay, all I have to know is how to prepare the beginning of the stack frame, and I know that this function doesn't return a value, so when it returns, I don't have to copy EAX into anything, and then I will, restore the stack frame. Okay, so the compiler can actually generate code for this without knowing anything about subr, other than, it takes, arguments and things like that, right? So it needs the function prototype over here to say that subr is a function that returns nothing, and it takes one argument that's an integer. Okay, that's all compiler needs to know in order to generate code for main.o. Okay, later on, the linker is going to say, hey, so when the compiler generates code for main.o, it says call subr, but it says, I have no idea where subr is, but linker is going to figure it out. Okay, so it's going to leave a hole right here. The linker, when it eventually put all these things in memory, will get the address for subr, and it's going to, stick it, right here. All right? Okay, what about subr? This one gets separate compiling to subr.o. Okay, doesn't know how to compile this. Okay, so if you look at subr, right, it calls a C library function, printf. All right, so if you want to call a function, you need to know the function prototype, right? Otherwise, you don't know how to generate code for it. All right, so that's why we do pound include stdio.h, because in this header file, in the system header file, it tells you what the function prototype is for printf, so that it can generate code for printf, right? Again, push arguments onto the stack, and then do a call, and then this guy doesn't return anything. So when it returns, it will restore the stack frame to before the call. All right, so in this guy, this guy also know, how to generate code for it. So subr.o can be generated, but inside subr.o, there's going to be a hole to say, I have no idea where printf is. Okay. Also, subr.o says I have the variable x defined right here. All right. So we're going to see the code. Actually, what does it look like? Okay. In the end, what you do is that so there's a way to combine all these three steps together. Use GCC minus o prog. What this will do is compile main.c to main.o, compile subr.c into subr.o, and then invoke the linker. So this one actually does, all the separate compilation, but in one step. Our warm-up 1 and warm-up 2, I require you to do the separate compilation manually. All right? But in reality, this is done automatically. All right. So these are the program. Okay, we're going to see what kind of code get generated for these programs. All right? All right, so over here, some more notes, right? How does LD knows what needs to be done? Okay, so it must be inside the .o file, right? Because in the end, the LD just take all the .o files together and put them together, right? So that means that inside main.o, okay, inside main.o, it must say, I need to put the actual address of sub r right here, okay? In main.o, so main.o sort of has a language that describes where the holes are and how do you fill the holes. Okay, so that language gets parsed by LD. So LD, when it opens up main.o, it says, oh, that's the place I need to put the address in main.o. That's the place I need to put the address of x. Okay, so it needs to do all that. Okay, and those instructions needs to go into main.o. Right, so in the .o file, it contains the code for main. It contains, variables like this. It also contains a bunch of description for what to do for the linker, instructions for the linker. All right, that's what's in .o files. All right. Okay. Let's see a little more. Okay, and also in the main.o, right, it needs to contain a list of external symbols. So these are the ones that it doesn't know what to do when you compile them, and it also point to where the holes are. Okay, and later on the linker will fill them out. All right, the dreadful assembly code is back. Okay, so over here we look at main.c when it gets compiled into assembly code. Right, so usually the compiler generates assembly code. The assembly code gets fed into the assembler, and the assembler generates machine code. Okay, and last time what we saw is also assembly code. Okay, so this code shows that assembly code actually contains additional stuff. All right, and the additional stuff over here are drawn right above it. Okay, so we saw the code last time, the main stuff. So I don't really need to explain that again. Okay, the code looked very similar to what we had last time. Okay, but now there's extra stuff on top that tells you what goes into data segment, what goes into TXS, all that kind of stuff. All right. So this code is what happened when you compile this code, using GCC minus C. All right. So it would generate a module. Okay. So let's look at some of the details over here. Okay. Over here, the first column over here says offset. Okay. So we're doing separate compilation. Every module has a bunch of segments that it needs to describe. Okay, so it needs to describe what goes into the data segment, also what goes into the code segment or the text segment. Okay, so and every segment will start with location 0. Okay, because they are relocatable, so we can just assign them any kind of address, and later on we can move them around in memory. Okay, so when you do separate compilation, you don't have to know their final address. Okay, so we started out. We said, well, here's the beginning of the data segment. Right, what follows goes into the data segment. Okay, so look at this code, right? What goes into the data segment? The only thing that goes into the data segment is AX. All right, over here, so we say there's a global variable called AX. Okay, global means that this particular symbol is exported. Oops, I need to go back. Okay, global meaning that this AX symbol can be used across all the other modules. Okay, so again, you write it into the .o file indicating that AX is an exported symbol. All right? So what else is exported over here, right? When you write your C program, anything that doesn't say static in the beginning, they're all exported. Okay, so in this code, AX is exported. Also main over here main, we didn't say static main, right? We say int main. So main is also exported. All right, so external stuff can see main. They can also see AX. All right? Okay, so that's one thing. All right, and then over here, there's another line over here that says .text. Okay, so starting from here, everything is in the text segment or the code segment. Right, so this tells you that later on, when this thing goes into memory, okay, here's the text segment, here's the data, here's BSS, right? What about the heap and the stack? Well, the compiler and the linker don't care, right? Because they are created on the fly. In the beginning, you know, when you try to compile, you don't really, you just know that the stack is going to be there and the heap is going to be there. Okay, so in a .o file, all we worry about is what goes into the text segment, the data segment, and the BSS. All right. So over here it says, you know, the following goes into the text segment. So here's main is going to be, you know, somewhere in the text segment. Okay. Also, the global symbol main is going to be exported, you know, from the text segment. All right. So that's what these things are saying. Okay, the offset over here gets started because the segments are relocatable, right? So over here, when I describe the data segment, I start with location 0, right? So the variable AX has location 0, okay? And over here, when I restart the text segment, it's relocatable. So the first instruction in the main program is also at location 0, all right? It's okay, they're both at location 0 because later on I'm going to move them around, right? I know that these addresses are not permanent, okay? So that's okay for them to start at the same place. Global describe what's being exported, okay? And over here, all right, over here, at memory location 0, I define a symbol AX, right? Over here I said global, okay, here's a symbol, AX is global, and this is where you put AX. Okay, so where's AX? AX is in offset 0 in the data segment. Okay, so inside, again, here's the data segment, right? Text, data, okay? Data segment, there's something called AX. Okay, AX is 4 bytes long. Okay, over here it says .long. It says AX is 4 bytes long. And what goes into AX? Well, over here it says it's a symbol X. Okay, so symbol X, all the symbols are referred by their addresses. So over here, when I say X, I mean the address of X. All right, otherwise I need to actually copy the data from X into into this memory location. Well, that requires code. Okay, so over here, I just keep the address of X, so I really don't need code. All I need to do is to reference the symbol X. I said put the symbol X right here, okay, and that's 4 bytes long because it's that long. All right, so if you look at this code, right, I put AX right here, and then it increment the address in the data segment by 4. Get ready for the next global, the global variable. But in this example, we have no more global variable. Okay, so therefore the segment gets restarted, and then you start describing the text segment. All right, so everything over here describe the first few things here. Okay, so what requires relocation? Okay, so this, this place requires relocation because at this point I don't know where X is. Later on, when the linker eventually decides where X is, it needs to come over here to offset 0 of the data segment. Right? So right now, the code that's get generated, offset 0 has a hole in there, 4 bytes long, waiting for the linker to fill in a real value. Okay? Because later on, right, when you try to execute the code, well, the code has to look like this. Okay? AX needs to contain the address of X. Okay? So if the linker doesn't really fix it, then when you start running the program, it will do the wrong thing. Okay, so therefore, when the linker creates the executable, it better make sure that this condition is satisfied. You need to determine the location of X, put the address of X in here, and then put it into this memory location, and this memory location is right here. Okay, so we're going to make a note in a .o file to say that this location is relocatable. Okay, what else is relocatable? Over here, here's an instruction, right? Over here it says move AX to EAX. Okay, because we have instructions over here says, we're gonna read the content of AX into Y. Okay, so this one, involve AX, right? AX right now is sitting at memory location 0. Why? It's because it's relocatable. So later on, AX will get a real address. Okay, so therefore, these few instructions right here, right, it takes about 3 instructions to copy the content of AX into the variable Y, and Y is EBP relative. So over here, it takes these 3 instructions, move AX into EAX, access EAX indirect, and then put that into EAX again, copy EAX into EBP. Those 3 machine instructions is equivalent to Y is equal to start EAX. That's right. Y equal to start AX. Okay, so over here, this is, this does not require relocation. This does not require relocation. But the first one has AX involved in there, so that one requires relocation. So again, in main.o, we need to make a note to say that AX at this memory location needs to be relocated. Okay, so how do we really say that, right? So what we need to say is that if you look at this code, this is the text segment, okay, and here's offset 6 is this instruction. You look up the Intel, manual, and it will tell you that this particular instruction is a 5-byte instruction. Okay, the first byte tell you that the instruction looks like this, and the second byte, contains a 4-byte quantity that says AX. All right, so therefore, what you do is that you write a little note to set in the text segment offset 7, right? 6 plus 1 is equal to 7. Offset 7, you got to put in the address of AX. All right, so that's what goes into the .o file, right? In the text segment, 7 location from the beginning, there's 4 byte, put in the address of X right there. Okay? In the text segment, offset from 0, put in there are 4 bytes there, put in the address of X into that memory location. Okay? And finally, over here it says subr, right? We generate all the code to set up the stack frame, and then we call subr. So over here, call subr. So again, this instruction is a 5-byte instruction on Intel. Okay? The first byte is the machine code for call, and the next 4 bytes are the address for subroutine. Okay? Again, you make a note to say that this memory location you need to be relocated. When you eventually figure out what the address of sub are, put it at the code segment, offset 19 plus 1 is equal to 20. Okay? Location 20, you need to put in the address of the subroutine. Okay? There's a little bit more detail over here. Is that Intel, for some reason, they don't use the absolute address of the subroutine. They actually use something called PC relative addressing. Okay, so the instruction pointer will be pointing right here when this instruction is executed. So actually, you need a difference between the memory address of subr and this memory location. Okay, so you have to take the actual address of subr, subtract the symbol for main plus 19. Right, because this is 19 into that particular memory location. You need to compute a difference and then stick that difference into this memory location. All right, so the .o file needs to know how the processor works, okay, so that the compiler will, so when you compile, you need to say that I'm compiling for the Intel x86 processor. x86 processor require a PC relative address over here and not an absolute address, while in memory location this and that, they need absolute address. Okay, so the .o file has all these kind of details in the .o file. All right, it's a lot of details, right? It's a strange language describing all these details. All right, so that's main.s. Okay, what about subr.s? Okay, so this is the code, right? Get compiled into this whole thing. All right, and you will notice that in here there's going to be 3 different segments. One is data. One is .com. So .com is BSS. Okay, so this is the data segment. This is the BSS segment, and then this is the text segment. All right, this example you actually see them all. They are in this file. All right, let's go over them. In the data segment, right? What's in the data segment? Okay, inside the data segment is X in the data segment. No, because it's uninitialized, right? Uninitialized global variable going to the BSS segment. Okay, so what goes into the data segment? So as it turns out that if you use a string constant, the string constant goes into the data segment, right? Because these are data, right? They're global variables sitting.
The time is 15 o'clock.
Where do you put a global variable like that? You can't put it in BSS, so you have to put it in the data segment, right? There's nowhere else to put it. Can you put it in code segment? Maybe, right? But it's really not the right place for it. Okay, so you will put this in the data segment. Okay, I guess these are dependent on the compilers. There are systems that will put the string in the data in the text segment. The difference between the text segment and the data segment is that the data segments are for data that you can modify. So the data segment contains things that you can read from them and you can write to them. Okay? If you put something in the text segment, then that means that it's read-only, right? I mean, you don't want somebody to modify your program, right? Because then the attacker can, if you worry about security, then you don't want virus to actually modify your program in memory. Okay? So therefore, usually you will protect the text segment, make sure they're not writable. Okay? So if you put this data into the text segment, well, that kind of makes sense because then you can modify the string. If you put it in a data segment, that means that actually somebody can actually modify it. So maybe that's not a good idea. Anyways, in this example, this string is put into the data segment. Okay? How big is it? Right? 1, 2, 3, 4, 5, 6, 7. Right? Backslash n is 1 character. And also you need a backslash 0 because these are C strings that are null terminated. So this one actually takes 8 bytes. Okay? So you can see that in the data segment, location 0 has the string constant, this string constant, okay, and it takes up 8 bytes. So therefore, the next location in the data segment starts at memory address 8. All right, so this guy takes up 8 bytes, goes into the data segment. All right. Okay, in this example, I actually create a symbol called printf arg. Okay, so what happens is that when it compiles this program, any kind of a string constant, it will allocate space in the data segment, and it will assign a symbol to it. Okay, these symbols are only, sort of temporary to the compiler, so outside world doesn't really have to know. So in this example, we use printf arg as the memory location for this, and this symbol is not exported, right? You don't see anything that says global for printf arg, so this symbol only makes sense inside this particular module. Okay. And over here, I do push out printf arg, referring to this memory address when I call printf. Okay, when I call printf, right, this becomes functional arguments. I need to push them onto the stack. So therefore, I'm going to push the address of printf arg onto the stack. Okay, and again, this memory this location is relocatable, so you have to make a note later on. Okay, but what the point over here is that when you try to use such a string constant, you use the address of the string and you pass it along. Okay. All right. Over here, this one take care of inx. Right. Inx is in the BSS segment. So over here, I say .common, and I declare a variable x over here. So if you use .common, .comm, that also means that this particular variable is in the common area, and it's global. Okay, so this one also export this symbol to be a global symbol, and it says this guy is 4 bytes long, and there's no initial value because it's in the BSS segment, it doesn't have to be initialized. All right? Okay, finally, the subroutine symbol, right, sub-R symbol, right here, this guy is exported. Okay, and in the beginning, for this module, it starts at location 0 of the text segment. What else? Relocation required for what, right? So over here, the access printf arg. Printf arg is going to get a real memory location when the linker put these things in the right places. So this needs to be relocated, right? And again, the location that needs to be filled in with the actual memory address is going to be location 7 of the text segment of this module, right? And also over here, you call printf. I don't know where printf is, or this module doesn't know where printf is. Call printf is a 5-byte instruction, so location 12 needs relocation, and it needs the memory address of the printf function. All right? All right, so in the end, you sort of see that, what's inside, what's inside of a program, right? The program eventually gets compiled into, something like this. Okay? So the only thing that you have, are data and addresses. All right? There's nothing else. Okay, so in the end, the executable program, right, when you put all these .o files together, resolve all their addresses, all you have are data and addresses. There's nothing else. Okay, so when you write C++ program, you go methods and objects and things like that. They're all illusions that got created by the programming language. Okay, in reality, when you need to hand a program to the operating system to execute, right? execl, here's the program. That program only contains data which are bytes in the data segment and the bytes that are in the code segment. Okay, plus a bunch of symbols. All right, and the symbols are addresses, and that's all you know. All right, and that the operating system can deal with. All right. Okay, so that's sort of the detail of the assembly code, the meaning of all those lines in the assembly code, and now we're going to see what goes into the object file. Okay, the object file describes what goes into the data segment, the BSS, and the text segment. Right? No stack, no heap. All right? So every object file, so this is a .o file. Okay? It has 3 sections to start with. Okay? The text, the data, the BSS. Right? And the text start with .text. Okay? Data.data and BSS.comment. All right? And then there are other descriptions that goes in here. All right, along with each section, well, actually over here, I guess this picture is not right, is that along with every section, there's a description. Okay, the description tells you what to do with these segments, what needs to be relocated, what address needs to be put in what memory location. Okay, and of course, BSS doesn't really have that part. Okay, BSS just, it's just a bunch of symbols. Okay, so every section, it declares what symbols are exported, right? These are global symbols. What symbols are undefined, so later on they need to be relocated, okay? And then the detailed instruction for relocation. What type of relocation does it need? And what do you copy over here? Is it PC relative address or absolute address, etc. And they all go into that description, the description. Okay, so actually, you can take your .o file and run through a bunch of things that can examine an object file. Okay, one thing that you can do, the simple stuff, is to run the nm program. So you say nm, okay, my 402 list.o. Okay, so this will tell you, it will list all the symbols in this object file. All right, you're going to see inside this object file, the output will tell you which symbols have resolved memory addresses and which symbols have undefined memory addresses. Okay, so in your, I guess in your my402 list.o, what kind of stuff is unresolved? Well, anyways, you probably should do an nm and try to see what's in there. Okay, another more serious program is called object dump. Okay, you will use object dump in kernel 3 because you have to know what an executable program look like, so you know what to look for when you execute your program. Right, so kernel 3, right, you need to run a user program. Okay, so you need to sort of complete the implementation of execl. Execl, right, so if you start with, here's your program you want to execute, for example, hello world, right? Okay, it's sitting on disk, okay, and then, a program called, execl, hello world, okay, and now you go into the operating system is going to read this file, okay, so the parsing of stuff you don't have to do because that's outside the scope of this assignment, luckily. So then what it will do is that it will need, your code need to create the address space. Okay, when you create it, why do you need to create the address space? Right? Because you want to make this program run. Okay, so by parsing this file, you find these components inside your program. Okay, you need to create an address space, right? So this is your program, hello, that's executing, right? We sort of have a conceptual idea what the address space look like. Okay, now in kernel 3, you have to build the address space so that you create this illusion that the text segment is right here, the data segment is right here, the BSS segment is right here, the heap segment is right here, the stack segment is right here. Okay? And then you will be able to execute your program. And how do you execute a program? Well, when your program starts to run, all these memory locations, they have to be in memory. Okay? So in order for you to really know that you did the right thing, you got to go to the memory location and verify that these things are there. Okay, so that's what sort of bulk of the difficulty in kernel 3 is to make sure that these things happen correctly and you'll be able to verify. So in order for you to know what should be in memory, well, you sort of need to know what goes into the object file. Okay, because that will give you enough information so that you can inspect these kind of stuff to know what should be there. Okay, so the object dump will actually give you a dump of this object file so that you know what, from the point of view of the user program, what does memory look like? Okay, if you need to know that, if you want to debug, right? Debug, you say, well, when I try to execute code, I just get a segmentation fault and my user process dies. You say, well, did you really execute code or you execute garbage? Okay, so that's the kind of question you need to ask. Well, how do I know that I actually execute code? Okay, what does code look like? So you have to know, right? That's what debugging is all about, right? You have to know what to expect, and then you verify that, what you're expecting is there. Then you know that your program should execute correctly. Okay, so the reason that we need to use object dump is that we're going to have a dump of the executable file, and later on, when you run your user program, you can verify that the user program, that's what it sees as well. Right? If the user program sees what it's supposed to see, well, then it should execute fine, right? Okay, the user program won't be able to execute if what it's supposed to see is not there. Well, then it's going to execute garbage. All right, so anyways, you're going to get good at object dump, in kernel 3. So for now, you can sort of play around with it. And if you read the kernel documentation, it will give you some idea of how to run object dump to examine executable files. All right? All right, and also right now, it looks like this is too hard. How can I do that? When you get into kernel 3, you'll be able to do that. Okay, trust me. That's the good news. Okay, all right, let's get back to this. The relocation is required over here. So how do you put that information into that .o file? Okay, if you run object dump or something like that, you will see the actual description. But of course, if you look at the binary code, then it's not going to make much sense. Okay, so we're only going to look at some high-level description of what goes into the object file, and we're going to trust that that information is represented in a reasonable way so that linkers can deal with it. All right. So in this example, we have two locations that needs to, two addresses that needs to be relocated. Right. One is at memory location 7. Right? Remember, this is a 5-byte instruction. So starting at memory location 7. Relocation required, and you need to put the address of printf arg in there, and then at location 12, you need to put the address, you put the symbol printf in the memory location. Okay, so in the subr.o file, okay, so over here, this is what you see when you look at subr.o. Okay, you see that it has data segment, it has BSS, it has text segment. Inside the text segment, there's some description that goes along with it, and it will say. At offset 7, there's 4 bytes. Okay, what needs to go in there is the address of printf arg. All right. Also, at offset number 12, there are 4 bytes over here. What needs to go in there is the PC relative address of printf. All right. So with all these descriptions going in there, the linker can figure out what to put in those memory locations. Okay. All right. What else in here? The global variable is also described over here. So these are the exporter symbol, right? X is exported, subr is exported. So over here, inside the data segment, it's going to say the global variable X over here is exported. So there's an exporter symbol called X, and it's at memory location 0 in BSS. All right, and whatever I move BSS to, I need to keep track of where that is, and that's going to be the new memory location of X. Okay. Over here, it says subroutine, okay, subr is also a symbol that gets exported, okay, the current memory location is at offset 0 of the text segment, okay, when I find the final place for it, I'm going to use that final location, all right? What else? Over here, location that are unresolved, right, these are unresolved symbol, they also go into, so now we're looking at the main program, right? Main program, there are 2 external symbols. One is X, right? And the other external symbol is subr over here. Okay, so those things are unresolved. Okay, so we put it in here. And inside the data segment, we're going to say that inside data segment, there's an undefined symbol X. Okay, and already mentioned what do you need to put in there when it's eventually resolved. Also, there's a symbol subr over here is unresolved. Okay, we also mentioned already that how to use the symbol once it got resolved. All right, so all these things sort of tie together. In the subr.o, there's an undefined symbol, right? The undefined symbol is printf. Okay, so over here it says printf is undefined. Okay, and we already also have instructions of how to use that after printf is resolved. Okay, so all these things are in .o file. All right, so over here it says printf.o. Where's printf.o? Okay, printf.o is in the C library, right? Okay, so what happens now when compiler goes to work, right? The compiler has main.o, and then it has subr.o. Okay, and it has all these description in here, and it also the compiler has access or the linker when it try to finish when it try to perform resolution and symbol resolution and relocation, right? It has access to all the libraries. If you say -L something, right? If you say -L RT, okay, you're telling the linker I need to look for a file called librt.a, right? .a is a library, okay, so the linker actually know where to look for these things. Default location is /lib, okay, also there's /userlib, /userlib. Okay, so the linker needs to know that it needs to find this particular library, in these standard locations. Okay, what does it do when it goes over here? Right, again, in a library is just a concatenation of a bunch of .o files. Okay, so over here, it's a collection of .o file. Inside the .o file, there's going to be a bunch of, again, what is in .o file? Well, it's exactly the same as these .o files. Every .o file has text segment, has data segment, has BSS. So therefore, what it will do in this case is try to find the function right in one of these libraries. Okay, I think the system call, there's a system call library. Maybe they're part of the C library. So when you compile, there's a hidden -lc that get executed. So what it will look for is libc.a. Okay, and libc.a I think it's in /lib. Okay, and inside this one, there's going to be many .o file. One of the .o files is printf. All right, so it's going to go to printf, and then it will read the code from printf and copy that into your executable. Okay, again, here's your LD program, right? It takes this as input, takes this as input. The output is going to call prog. Okay, so this is sitting on disk, right? It will try to write to this prog thing. It will create a text segment, create a data segment, create the BSS segment. Okay, and what it will do is it will also read /lib/libc.a. Okay, it will take this file. There's a function over here called printf. All right, and again, what's in printf? Printf, just like main.o and subr.o, printf has data segment, has text segment, has BSS, right? So you need to take that entire thing and then copy them into your program. Okay, so the printf function will go in here. Okay, so now when you make that call, you know where that function is because it's inside your text segment. So you have to copy that program from libc.a into the executable program. Okay, and if over here there are also global variables, you need to copy them right here. Right, and when you copy them, you get an actual address, and that's when you figure out the relocation where these addresses are going to be. All right, so over here again, printf contains a bunch of information. It has data. In this case, there's actually 1,024 bytes of data that needs to be created over here for printf. Okay, BSS, it needs 256 bytes over here, right? Again, so the linkers try to figure out what is the size of the text segment, what is the size of the data segment, what is the size of BSS segment by concatenating all these .os together so that it knows exactly where does one segment, end and the next segment begins. All right, and for every one of these symbols, you need to figure out what the actual address is for every one of these symbols. All right. Okay, so the text segment for printf is pretty big, 12,000 bytes. So this function is actually pretty big, sitting here 12,000 bytes. Okay, this guy also has an undefined symbol. Okay, so write is undefined, right? So again, the linker will continue to work over here, find the write function over here, copy write into here, right? That takes us into the next page. Okay, write.o is right here. the data size is equal to 0, BSS take another 4 bytes into BSS, so BSS is going to keep expanding, and then the code itself is only 16 bytes long. Does that make sense? Write is only 16 bytes long. Right? Remember, the system call are just wrappers around the trap machine instruction. All right? So this is this write, right? All it has is set things up, trap into the machine instruction. When it return, it fixes the return code, and that's it. So therefore, this this function is very small, and that makes sense. Okay? So over here, again, in write.o, they have the code over here. So it's the linker's job to copy all that code into the text segment of the program. All right? So do we have everything? There's one more thing, right? We need a startup function, okay? Because we have nothing that will invoke main, okay? So we actually have to go to one of the standard library plays, look up the startup function. The startup function takes no data, no BSS. It takes 36 bytes long, right? So what is it doing in 36 bytes? In 36 bytes, what it does, it calls main, right? It passes the arguments to main, right? argv, argc. So it needs to create the stack frame for main, invoke main, and when main returns, it needs to call exit, right? It takes the return value in EAX and then pass that to exit, and then it's right there, okay? So over here it says undefined is, it calls main, so main is undefined. Actually, there should be also things like exit that's in here. Okay, and in the exit call also get sucked into your program. All right. So, anyways, so if we can also look at exit.o and see everything there. So you basically know how everything is found, right? In the end, you have this program prog right here has a text segment, has main, right? Has sub r, has printf, has write, has exit, has startup function. They're all in the text segment. Okay, data segment contains a concatenation of the data segment of main.o, the data segment of subr.o, the data segment of printf.o, write.o, exit.o, and the startup function.o. Well, actually, it's emptied over here. Okay, the BSS segment, right? The BSS segment, they're uninitialized. Okay, so it's just you need to create the room for it. Okay, so you need to make a note inside program to say that there needs to be this room for all these uninitialized variables. And the size of the BSS is going to be a concatenation of, or the addition of the size of the, the size of main.o, the BSS in subr.o, the BSS in write.o, printf.o, exit.o, all these kind of stuff. All right? So the linker can figure out how big this is, and how big this is, and how big this is. Then it will place all these functions in some random order into the text segment. So you don't really know where main is going to be. Okay, they can be placed anywhere inside memory over here, right? And the picture I drew over here, I mean, why do I draw it this way, right? I am using the abstraction of the address space, okay, to say that when this program gets loaded into memory, this is what it's going to look like. Okay, so therefore I need to sort of figure out, right, because at the time when I try to execute my program, when I load my program from disk into memory, I just want to load it as quickly as possible. Okay, I don't really want to, do additional linking or something like going on. So whatever that's on disk, I just want to copy into memory, and then, and then it will be done, and it's ready to execute. Okay, so therefore everything over here on disk has to be just right, so I can easily load them into memory. Okay, so the address space view of the user process says, over here, here's the text segment, data, and BSS. So all the functions are there, right? One symbol after another, they're all there. Okay. In the data segment, there are all these symbols that these code might reference, and they're all sitting at the right places. And the final memory location they got the final location they got when they are referenced in the program over here, they all get fixed during link time because the linker figure out what memory location they are, and then use the linker's instruction to fix those memory locations by putting the actual address into those places. All right. So again, the linker will take addresses, right? All you have addresses are data. It will take the addresses and put them into over here when it perform relocation. All right, and the BSS, that doesn't matter. You just need space for that. All right, so at this point, when your program is ready to execute, this is the end of these pre-allocated address space. Okay, the heap is going to start right here. All right, and the stack starting from the highest memory address, and the operating system know where the highest memory address is. All right, so this gives you the actual program. All right, so when we compile this program, right, the linker will produce this information, okay, and when you do object dump, okay, or when you do like or nm, okay, warm up 1 or warm up 2, right, you're doing a symbol table dump for warm up 1 or warm up 2, right? nm stands for mnemonics. So basically it shows you every symbol what is the address it has. Okay, so in this case you will get a dump of all the symbol table. Main is at location 4096. Subbar is the location 4132. Printf is here. I mean, okay, by the way, these numbers are I made them up. I think they're the same as in the textbook. Okay, but they're made up numbers. In reality, these might not be the actual address. Okay, so this one shows you that one is after another. If you go to main.o, you will see the size of main is exactly the difference between these two. There's no gap between all these functions. They're packed together to minimize the use of extra memory. Okay, so they're packed together, and this is the entire text segment. All right, and then comes the data segment. So the startup function is actually very small. I don't know if you remember, it's 36 bytes long. Okay, if you add 16172, add 36 to it, that should be equal to 16208. All right, you can see that there's a gap between that and the data segment. Okay, so again, the final address space, the text segment doesn't really start at memory location 0, right? So over here, there's 1024 bytes here, okay, and then comes the text segment, okay, and then there's another gap over here, okay. That's the gap between 16208 and 16384, okay? And then come the data segment, okay? And the data segment from here to here, I guess there's no gap, so BSS is right here. Okay, so over here at the bottom is some gap, and then there's a gap between text and data segment. All right, so again, these numbers, you can calculate them from the previous slides, add them all up, and hopefully you'll get the same number. All right? Oh, and also, I guess the picture wasn't completely there, right? Because, it wasn't really complete, right? There are also things like exit that are not in this picture, and the error number over here is added over there. Okay, because when you make a system call, inside the implementation system call, if there's an error, it's going to set the error number, so all these things are external symbols, right? Error number could be a function or it could be a global variable, it depends on the implementation. Okay, so in this case, it also takes up a memory address. All right. The reason that these gap is because modern operating system use pages. Okay, the data segments needs to start at a page boundary. Okay, so typically a page is 4 kilobytes long. Okay, or 4096 bytes. Okay, so again, if you look at this memory, 4096. Oh, why did I write 1024 in the last slide? It should be 496. Right, so the first 4096 is not used. Main starts at, so over here, 4096, okay? And the first one is main, okay? And another 4096, 4096, okay? Over here, these function, the main goes right in here, and then subr goes in here, printf goes in here, write goes in here, startup goes in here, and eventually it takes up all the way up here. Okay, and then there's a gap over here, and then the data segment starts right here. Okay, and data BSS starts right here, and then here is another 4096 page. All right, so modern system like things to be aligned on page boundaries. Okay, so that this is for efficient access. It's going to become more apparent when we talk about virtual memory. Okay, so for now, you sort of need to understand that the memory are actually allocated 4 kilobytes at a time. Okay, so therefore what we want is that we want to keep all the text data, all the code together into, in this example, 3 different pages, and the data in the BSS, we're going to put them in a separate page. Okay, and the reason for that is because of the following. Okay, so we're going to sort of describe, sort of the basics of virtual memory. This we're going to cover in, all the details in chapter 7. So at this point, we're going to say that, well, when you allocate memory by the operating system, the operating system is going to allocate 4 kilobytes pages at a time. Right? It could be different. Some systems use, half a kilobyte page. Some people use, 8 kilobytes page. But typically for Intel, we can say that they use 4 kilobyte pages. Okay? So these are the minimum allocation unit inside the kernel. Okay? So if you want to use 1 byte of memory, you're going to get 4 kilobytes. Okay? It's very, very wasteful if you only need 1 byte of memory. Okay? But that's the way memory are allocated. Okay? If you have a data segment and a BSS segment that's only 1 byte long, okay, it's going to take up an entire page. All right? If you have a code segment that's only 1 byte long, or if you have a code segment that's 4,097 bytes long, it's going to take up 2 memory pages. Okay? And again, we allocate 1 page at a time so that we can allocate these pages efficiently. Okay? So at this point, sort of efficiency is more important than saving memory. All right? It's always a trade-off. All right. So we allocate 4 kilobytes of memory. We allocate 4 kilobytes at a time. And these are called pages. Okay, certainly we don't want to allocate 4 gigabytes at a time. We don't want to allocate the entire address space for executable program. Okay, we only want to allocate the memory that are actually being used by that program. Okay, so if you think about the program that we're building, proc, right? Okay, the bottom is not used, and then we have 3 pages over here of code, right? This is the code segment, and then 1 pages of data and BSS. Okay, and then we have some, heap area, and then we have some stack. Okay, in the beginning, our program might be doing something not very exciting, print a message and quit. That's the example we have, right? They call sub-R, print a message, and it quits. Okay, so this program actually uses very, very little memory, right? So the stack space that I use might also only be 1 page. Okay, and this program doesn't use heap at all because it doesn't call malloc and, free, all that kind of stuff. Okay, so this program only needs 5 pages, to run. Okay, so 4K multiplied by 5, you need 20 kilobytes to run this program. If we allocate 4 gigabytes, that's really a total waste. Okay, and if you have 4 gigabytes, right, that's 2 to the 32. Okay, 4 kilobytes is equal to 2 to the 12. Okay, so how many pages do you have in the entire address space, right? Over here, we actually have 2 to the 20 pages. Okay, we have about 1 million pages in the address space. Okay, all we need are 5 to run this program. Okay, so therefore, that's why, so the kernel tried to be more efficient. Instead of allocating 1 million pages or entire 4 gigabytes of memory, allocate, 20 kilobytes, which is 5 pages. All right, so this way, to support the running of this program, it only needs, 5 pages. All right, so in the end, even though they are inefficient and it seems to be wasteful, in the end, they actually save a lot of memory. All right, so that's why in the modern system, they're all sort of implemented this way. Okay, we use page table in virtual memory, so the operating system is got to allocate pages at a time, so they cannot allocate something that are off page boundary, right? So the pages go from 0 to 4096, okay, and then the next one go to 9192. Okay, you can't say I want a page that start from halfway over here and go across that, because every time when you allocate memory, it needs to be aligned to page boundaries. Okay, so if you look at the virtual addresses or the physical address, page aligned address, meaning that all the least significant 12 bits, they're all 0. Okay, so if you get an address, the last 12 bits, they all have to be 0 for the address to be page aligned. Then you have an address that are at the page boundaries. Okay, and that's how how this memory works. All right, so a page is 4 kilobytes in many systems. Okay, and a page corresponds to physical memory that can be allocated anywhere in virtual memory. Okay, so that's also very important, right? We're going to use some sort of a memory mapping system to map these 3 pages, each one of them individually, to a physical page of memory. Okay, so virtual memory, we're going to chop them into pages, 4 kilobytes each. Physical memory, we're also going to chop them into 4 kilobytes each. And then we're going to say that, well, this page is going to map to somewhere in physical memory. Okay, doesn't matter where it maps to. Okay, as it turns out that if you do this one level of indirection, okay, and if you always point them to the right place, then the place that it gets mapped to can be anywhere in physical memory. Okay, so in physical memory, this page might be sitting here, this page might be sitting here, and this page might be sitting way out there. All right, but in virtual memory, which means that virtual memory, meaning that that's the view of the application program. The application program only see virtual memory because everything is sort of faked, by the OS for the application. All right, the application see that these addresses are contiguous. Right? If you go from this address, if you add 5 to it, you get the other one. But it turns out that the other one might be in a physical place, a completely different place. Okay, so we're going to use this virtual memory scheme using something called page table to map virtual addresses to physical addresses, or to map virtual pages to physical pages. And then these physical pages can be located anywhere as long as you point them correctly using the virtual memory map. All right, so this way we have a lot of flexibility, and also we can allocate only a small portion of the address space. All right, so this idea of indirection, as you see again, is very important in the operating system to make things flexible and fast, and also save space. All right, so that's kind of like the brief introduction, because we're going to spend a lot of time talking about virtual memory. Okay, so this picture shows you what the page table look like. Right, page table is this map from virtual address, which means that the address the user program sees, and the physical address is where the actual physical program is sitting. Okay, so over here it says, all right, so here's the page table. It says location 0, right? So all these addresses need to fall on page boundary. Location 0, there's no access. So if you read or write at location 0, you're going to get a segmentation fault because it says no access. Okay, so when you try to access memory location 0, that memory location 0 needs to go through this page table to get translated into physical address. In that case, the translation will fail because it says you're not supposed to access that location. Okay, that's why you get a segmentation fault. Okay, for the next 3 pages, they are code. They are code. Okay, so starting at location 4016 all the way to 16383. These are code segments, right? So all these code are sitting in these 3 pages, okay? And these 3 pages over here, the page table says they are read-only. Okay, so if you write to these memory locations, you're going to get a segmentation fault again, saying that you're not allowed to write to these memory locations. Okay, and finally, these things that are actually mapped to physical memory. So therefore, in the page table, okay, we're actually going to point this this page to the place in physical memory where data for this page is stored. Okay, so main is right here, right? So somewhere in here there's going to be main, somewhere in here there's going to be sub R, somewhere over here is going to printf, right? Printf is actually going to go all the way into, spill over into this guy and spill over into the next 2 pages. Okay, so if you follow the next pointer, the next page is going to be right here. So we have some of the printf code over here. The next page, right, is this pointer. This pointer tells you to map to this physical memory. The printf code is going to be here, and then the write code is going to be here. The startup code is all going to be here. All right, so over here, they're actually in the function printf, one instruction is in here, and then maybe even part of that instruction is on this page, and the other part are right here. All right, so this physical memory can be located anywhere. They don't have to be contiguous. The logical address over here, or the virtual address for your user program, they look contiguous, but by the magic of page table, they can actually be spread around all over memory. All right? So that's a text segment. And then we have the data segment of BSS. Over here, 16384 is the first memory location of the data segment. Okay? It's big enough to hold all the data in BSS. Over here, it says the access is read and write. Okay, so these memory locations, if you try to write to it, it's perfectly fine, which is supposed to be, right? They're rewrite. Okay, they also point to this memory location where all these global variables, they sit in this physical page. All right, so according to this picture, this is why there's a gap between the text and the data segment. Okay, because you cannot say the data segment will start at the location right after startup, right? Because that means that, well, if I start right here, then what should I set the access protection to be? Right? Because part of it is going to be read-only, and part of them is going to be read-write. Well, I don't have that flexibility, okay? Because I'm using this page table system, I can only protect one page at a time. So this page, if I protect it with read-only access, that means that I cannot make part of it rewrite. Okay, so therefore, all of these things that are rewritable, they need to sit on a separate page that are protected using read-write access. All right, so that's why, data in the BSS segment, they need to start at a different page boundary. Okay, then I can play around with page table to protect all the code segment. Okay? All right, so that's the end of linking and loading, right? So I guess later on we're going to come back to this picture again because it's sort of an important picture. We need to understand a little more. All right. Okay, so now the next thing we're going to do is we're going to get into Chapter 4. Okay, we're skipping a bunch of slides in Chapter 3. Some of them will be covered in the Wednesday afternoon lecture when I do a pre-tape. Okay, so that includes memory allocation and booting. Okay, all right. For now, we're going to start looking at Chapter 4. Right, with I guess when we begin Chapter 3, we said we're talking about this glue between the user program and also the kernel, right? And that including the linker and the stuff that's doing all the magic in between. And now we're going to look at the operating system design. Okay, so Chapter 4, they're talking about sort of design. They're really not talking about implementation. Okay, so we're sort of providing some reasonably high-level picture of what the operating system looks like. How do you divide up the operating system, looking at different kind of components? How do the components work together? And also some of the important concepts inside the operating system implementation that will make some of these magic happens. All right? Okay. All right. So I guess I mentioned that we're going to look at what goes into the OS, how do they tie together, how are system structures, and also over here it says how the performance concerns are factored in. Okay, the operating system in the end has to perform really well, okay, because otherwise somebody's going to use a different operating system. Okay, so performance become very important, and that's sort of where we need to introduce the performance trade-off. Is that there are many ways to do something. There are 5 different ways to do X. Which way is the best way? Okay, and usually the answer is there's really no best way. If you choose the first way, you're trading off something with something. If you choose the second way, there's some other trade-off. There's always some trade-offs. Okay, so in the end, you probably have to ask, well, your operating system, who is it for? Okay, is it for certain kind of users? If it's for certain kind of users, well, maybe this choice makes more sense. All right. In this class, okay, so anyways, I guess that's on the next slide. So we're gonna look at all these detail of different operating system components in Chapter 5 through 7, right? Those are the meat of this sort of this class, telling you how these things are implemented. Okay, but also the higher level picture are also very important. Okay, we'll start by talking about a very simple hardware configuration, and these are what the operating system that we need to deal with. So this is again we're going back to 6th edition Unix. Okay, 1970, 1980 Unix, and that's what our kernel assignment is kind of implementing something like that. We're going to sort of briefly mention what kind of stuff goes into the modern operating system, but mostly we'll sort of talk about the foundations of your operating system. All right. All right, the application, look at the operating system as what, right? The operating system thinks that it's running on real hardware. It doesn't really know about the operating system, right? It makes system call thinking that, something's going to happen because you use those kind of stuff to get access to hardware. Okay, so it thinks that it's accessing hardware directly, but we need to put in this particular layer. Okay, so the operating system, in order to provide that abstraction or that illusion, it needs to provide these kind of stuff reasonably in a consistent way. And it needs to provide a usable interface. Okay? And what are these interfaces? Well, the interface are the system calls. Okay? The system call I mentioned, there are 256 of them, so you can't really come up with 1,000 system calls, right? Then become very, very confusing. Okay? I guess even though Microsoft sort of takes that approach, Microsoft says that, well, the operating system, we don't really want to deal at that particular level. We're going to build another layer on top of the operating system, and that's going to be your operating system, right? So that's the what do they call it? I guess they have so many different names for it. I guess it was ActiveX, and these days it becomes an object-oriented layer so that you can actually program on top of that object-oriented layer. Okay, so in order to learn the Microsoft way of dealing with the operating system, you need to learn thousands and thousands of ways to get into the operating system. Okay, so we're talking about this sort of simple system call approach to interface with the operating system. Okay, so you're limited to a small number of system calls. So you need to be consistent, you need to be usable, it needs to be small, while you need to provide security. Right? Again, security meaning that the user processes are protected from each other, and also the operating system kernel is protected from the user processes. Okay? And you need to be efficient, right? You can make a really, really secure system, but the downside is going to be inefficient. Okay? So to make it both secure and efficient, that's really, that's really a tall order. Okay? So we're going to see what have we learned in the past 50 years, how to build an operating system. How are things done in the operating system? All right. So as I mentioned, that you need to ask, what kind of an application needs to run on these operating system. For this class, we are focusing on general purpose operating system. Okay. So these kind of operating system, and the reason is that if you want to build a special purpose operating system, it's actually not that interesting because if you want to build an operating system that just do one little thing, just bypass that operating system and just build that one little thing. Okay, so you can actually make anything works with a special piece of hardware. You can write some assembly code, provide a few function interface for your application program, and that's your operating system. Okay, so writing special purpose operating system is really, not very difficult. All right, writing general purpose one that needs to work well for all kinds of stuff that's supposed to run on your hardware, that turns out to be kind of tricky. Okay, so we need to run a variety of applications. Some of these applications are interactive. The user needs fast response. Some of these applications use network communication. Okay, and some of these applications rewrite the file system, right? And pretty much everything is sort of rewrite to the file system or across the internet. Okay, so the system that we are looking at is like most general purpose operating system, right? And these days in the market, what do we have? We have Linux, we have Solaris, we have FreeBSD, we have Mac OS X, we have Windows, we have Chrome OS. We set up, most of these stuff are based on Unix, right? The only thing is Windows. Windows are based on Unix, cousin, VMS. Okay, so we sort of focus on, Unix. Okay, all these operating systems are very similar. All these general purpose operating systems are very similar. They all provide, these kind of abstractions, right? Processes, okay, so that processes, this way the user can be protected from each other, right? So processes are used to provide protection, okay? We have threads. Threads are the ones that's running the code. We have from file system, some kind of abstraction, so that you don't have to know the detail of disk and stuff like that, okay? Network protocol with very similar, simple APIs. So actually these days when we talk to the network, the API looks exactly like the file system API. Well, pretty much, right? If you want to talk to across the internet, you open, a file descriptor, you read and write, and that's it, you close it. Okay, so pretty much the same thing as a file system. Very simple user interface, okay? And then we also have graphics, user interfaces for display, keyboard, and mouse, okay? And then finally, there's one more thing that are very common, access control based on file ownership, and the file owners can control. Okay, on Nunkey, if you want to, you create a file, okay, and you want your friend to access it, can you do that? Okay, as it turns out, there's a command called chmod, okay. This one changed the mode of a file, changed the protection mode of a file. You can actually say, I want my friend who is logged in as a different user, look at this file. Okay, so you can actually do that. Okay, so you are the creator of this file. You get to control who have access to your files. Okay, so that's what's used in common operating system. There are other operating systems out there, like the military operating system. The person who created a file has no control who can access the file. Okay, there are actually cases where you can create a file, and as soon as you create it, you don't have the clearance to look at it. Okay, so those are kind of weird systems, right? But those are not the systems we're going to talk about. Okay, all right. The operating system design issues are, it needs to be efficient, right? So performance, performance issues. It needs to be modular, okay? When we write our program, we divide things into modules, right? So that's part of modularity. And also you want to design your system to have system components. The components need to be modular. right? So you have this component, that component, okay? These components interact. When they interact, they need to follow certain protocols, okay? And usually when you design a system to be like this, it's going to be inefficient, right? Because instead of this guy read memory location deep down inside this module, you have to go through a protocol to actually get it. Okay? So when you try to make things modular, usually it's less efficient. But why do we like modular program? Right? It makes programming of the operating system a lot easier because if you want to deal with something over here, you just need to go through the protocol. This guy can be re-implemented with something completely different. You don't have to change the code over here. Okay, so modularity makes your system more maintainable, and that's why we like modular system, but we know that it's going to kill efficiency. Okay, so it's kind of hard to design both for modularity and also efficiency. We need to be device independent. Okay, every time we're adding a new device, right, the new device is going to come with device driver, and we're going to, how do we execute new, use new devices? Okay, we don't want to modify the operating system anytime a new device device driver came along. Okay, we're going to make sure that operating system can talk to all device drivers. Okay, so this way we can achieve device independence. All right, security I mentioned already. Isolate operating system from the application, and isolate application from each other. Okay, so the simple system we're going to look at, right, mostly in this class, are something like this. We have a network interface, talk to the internet, okay, and we have a CPU, and we have memory, okay, and then we use a disk, okay, and then we use some sort of a clock, okay, this kind of alarm clock that can give you interrupts, right? So one thing that you can do is that if you have a thread running inside the processor for too long, you want to kick off that thread, right? So one thing that we can do is that we can allocate quota and something like that for these threads. So when the thread starts running, we set the alarm clock. When the thread runs too long, the alarm will go off, and then we can switch that thread out, and put in another thread. Okay. So this alarm clock allow us to preempt. Okay. Allow us to preempt an executing thread. Okay. So it turns out to have an operating system that's preemptive is very important for the performance of the operating system. Okay, if you have a preemptive operating system, your system tends to perform better. Okay, so that's why a modern operating system, they all have preemption. And later on, when you do the kernel assignment, you're going to find out that our kernel assignment, we do not allow preemption. Okay, because preemption is complicated. So therefore, our kernel assignment, we don't have preemption. Okay, all right. Anyway, so it's a little weird. Because it's more easy to think about preemption. If you're using up to the processor for too long, you're going to get kicked off. So, our system can always make progress. Okay? What if you have a system where one thread doesn't give up the processor, and it goes forever? Okay, so let's say that that thread is something that you wrote for kernel number 1, okay, and your thread never give out the processor. What's going to happen to your operating system? It's going to hang forever. It's going to deadlock forever. Okay, so what happens is that in kernel 1, we don't have preemption, so we actually will allow the kernel thread to behave very poorly by hogging the processor and then deadlock the entire operating system. All right, so if that happens, whose fault is it? Well, it's your code, so it's your fault. All right, so one thing that you're going to notice in kernel 1 is that, my operating system deadlock. What could it be? Well, it's your code. All right, anyways, so we're going to have memory over here, right? We're going to use some bus for the processor to talk to the memory, and we're going to use a memory map. Okay, so this one is like a map, right? So it's a memory map. So we're going to use a virtual memory system to map virtual addresses to physical addresses in order to access primary memory. Okay, we don't have direct access to primary memory. It has to go through a map. All right, well, again, we're going to talk more about that in Chapter 7. The device that we're going to be accessing, the device, so there's a networking device, right? There's also a terminal device. The terminal device has a display, has a keyboard. It might have a mouse. We're not going to talk about mouse very much. The way the mouse works is that every time you move your mouse, you generate an interrupt. Okay, and you're going to talk to the device, says, what did you just do? Oh, I move, 2 centimeters, in the northeast direction or something like that. Okay, so your operating system can actually use that to figure out where is your, the current pointer location on the screen. Okay, so anyway, so there's the terminal and there's the mouse. Okay, And they might use something called USB protocol to sort of, use the USB protocol in order for the operating system to communicate with this device. Okay, so what does the USB protocol does? Right, remember, if you plug in let's say a flash drive into your laptop, right? The first thing that you're going to see is that it will say that, oh, I just discovered a device. Okay, and then what it will do is that it will download the device driver from the device into the operating system. Okay, so this way you can actually dynamically load a device driver, okay, into the operating system, right? And we just talked about linking and loading. Okay, so linking and loading, right? Loading meaning that you're going to copy that code and whatever data segment that it needs, whatever BSS that it needs, and we're going to copy the code into the operating system kernel, into running memory, right, into part of the address space. If you want to run code, you have to be in part of the address space. Okay, so the operating system, right? So again, this is the operating system now. The operating system also has an address space. Okay, it has, I'm not going to draw the text segment at the bottom. It has text segment, it has data segment, it has BSS. Okay, when you load a device driver into your address space, well, you're adding the device driver into the text segment. Okay, so all that thing needs to be done very, very carefully, right? Because you don't want to cause any kind of a relocation. So maybe those code will go somewhere else. All right, and they have their own data segment, their own BSS. Okay, and we're going to use the USB, right? USB is the protocol that you use to take the device driver and then install it into the operating system. All right, so that's why these days, all these devices, they use the same protocol because there's one common way to take a device driver and install it into the kernel. All right, so this is the kind of stuff that we're sort of dealing with, and this is the Ethernet at the bottom. Okay. All right, so the operating system component, right? There are lots of components in the operating system. Okay, so again, we draw this picture I saw before. Above this line is application space. Down here is operating system space. Operating system has many components. The important ones are chapter 5, 6, and 7. So chapter 5 is process management, right? Processor management is right here. Okay. Chapter 6 is about, dealing with the IOs, specifically the file system. And chapter 7, sorry, this is chapter 6, and chapter 7 is virtual memory or memory management. Okay. There are other stuff. I guess some of the stuff get covered by chapter 9 and 10. But we, I guess, we have a short, I guess our semester is always not long enough to cover chapter 9 and 10. Okay, so there's some, networking, subsystems out there that the operating system deal with. So there are more stuff out there. All right, so a little closer look at some of these operating system components. Okay, we're going to break them down a little more and see how they, sort of interact with each other. Okay. Here's processor management, here's memory management, and here's I/O management, okay? And there's additional division over here, okay? We're going to support, okay, multi-threaded processes. Each process has its own address space, okay? So over here, we're gonna put together between memory management and processor management. There's this crossover. That's where we put the management of processes and threads there. Okay, every process can have multiple threads. Even though I get this question a lot in the kernel assignment, the kernel assignment Unix, there's an option to implement multi-thread per processes. Okay, by default it's turned off. Okay, I suggest you not to turn it on. Okay, so in the kernel assignment, you're going to implement every process can only have one thread. Okay, it's going to make your life a little easier, so you don't have to deal with the complexity of multiple threads. Okay, after the summer session is over, if you want to turn on multiple thread per process, go ahead and have some fun. But for the sake of the the programming assignment, which you have to turn in and get graded, keep the multiple thread per process off. All right. So the kind of stuff that we're going to talk about in class is going to involve multiple threads per process. All right. Okay, and every process is on address space. And the kernel, the operating system kernel, is one giant address space that's shared by all the kernel processes and threads. Okay, there are tons of kernel processes and there are tons of kernel threads. All right. We're going to support virtual memory, right? There's real memory and there's virtual memory. They need to be mapped from virtual address space to physical memory address. As it turns out that every user process is mapped differently. Okay, so over here, right, that's why in the memory management part, you also need to involve some of the processing stuff because every user processes, have a different memory map in order to map its virtual address onto the physical address. Right? Because if you're running a bunch of user processes, all these user processes, they all have main, right? What if main, they're all at the same location. So what do you map to? Right? Every main function you need to map to a different physical memory location. So therefore, every process needs their own memory map, okay? Need their own page table, all right? Okay, thread execution is multiplexed on a single processor. Okay, we're going to talk about cases where, what do you do when you have a single processor, and what do you do when you have multiple processor? Okay, so when you have multiple processors, scheduling actually going to become a lot more complicated. So we're going to talk about cases where you only have a single processor. When you have a single processor, how do you schedule all these threads running on a single processor? Right, because you have to multiplex all these threads onto a single processor, and we call thread virtual processor, right? So you're going to do a lot of multiplexing. This multiplexing is done by the scheduler, okay? So there's something called a scheduler that's doing all the scheduling, okay? The scheduler needs to decide who to run next, okay? So, and again, the operating system, has a lot of, sort of different queues inside. We have seen mutex queues, okay? We have seen condition variable queues, and we talked about every I/O device, they also have a queue. Okay, turns out for the processor, there's also a queue. Okay, so if you think about this, right, CPU is sitting right here. Inside the CPU, there's also a queue in front of it. Okay, these are threads that are sitting there. They are not waiting for anything else. Okay, they're not waiting for mutex to be unlocked. They're not waiting for I/O device to be completed. They're ready to execute. Okay, all they need is a processor. Okay, that's why they get on this queue. Some literature will call this the ready queue. Okay, so this ready queue are for threads that are ready to execute. Okay, in our class we call this the run queue. Okay, so this queue are for the threads that are ready to run. Okay, so this could be the thread that already own the mutex, or once they're waiting for the mutex, they got the mutex, they're ready to run, so they get into the run queue. Okay, so what happens when a mutex, what happens when a thread is removed from the mutex queue? Well, it gets moved into the run queue. Okay, and eventually it has to wait for its turn to get into the CPU. As soon as it gets into the CPU, they are in the, if you have a thread that already got the mutex, they're in the synchronization box, execute critical section code or accessing shared variables and stuff like that. All right, so they don't get from the head of the mutex queue directly into the CPU. When they get off the mutex queue, they come visit this queue before, waiting for the CPU to become available and then execute on the CPU. All right, so the scheduler is the one that manages this queue. The scheduler actually decides who gets to run next. Okay, so as it turns out, scheduler is very important as far as the performance of your machine is concerned. All right. Okay, you also have interrupt management over here. You have a file system layer on disk, right? So over here is show you several layers. The file system is sitting on top of logical I/O management, and the logical I/O management sit on top of physical I/O management or physical devices. Okay, so the devices are actually at the very low level inside the I/O management system. Okay, so as it turns out that in order to get this thing to work, this is a very, very complicated subsystem down here. Okay, in order to get it to work, we actually end up doing many, many layers of indirection. All right, virtual memory is one level of indirection. Well, it depends on how you configure your processor. There are cases might be many, many levels of indirection. Okay, whenever things get more complicated, then the solution in the operating system often is another level of indirection. Okay, this system is so complicated that over here there might be 5, 6 layers of indirection before you actually get to the device. All right, so we're going to see what some of these layers are in chapter 6. We're going to have a terminal, and that's the main interaction. So this terminal, without a mouse, you can actually just type in command, right? So it's actually like the Ubuntu terminal thing that you use. Okay, in Mac OS X, you also have something called terminal. They're all called terminal. In Windows, if you run, XWin32 or PuTTY, they have something that emulate a terminal, right? So the way that you talk to an operating system is to use a terminal where you type things into. Okay, so normally you don't really have a mouse device. Okay, but a terminal is enough for you to do a lot of stuff. Okay, so we're going to sort of stick to this terminal device. The terminal device, it's a text interface. There's no graphics. Typically 24 by 80, right? So there's 24 rows and 80 characters across. Okay, and then you attach this to a keyboard, right? Keyboard. Okay, every press, every character typed on the keyboard gets sent to the processor. Okay, so every time you press the key, you get an interrupt in the processor. The processor will, talk to the device driver. Device driver says which key got pressed, etc. And eventually, your data go to the right place. Okay, lots of things happen, for that one key press. Okay, similar thing as moving the mouse. If you have a graphical user interface, when you move the mouse, many things happen before you say, oh, the mouse just moved 2 centimeters or 2 millimeters, this way. All right. I guess this is for chapter 9 and 10. When you communicate, we use Ethernet these days. I guess a long time ago there were many different standards. These days, there's, pretty much Ethernet is the best way to go. And then you also have wireless communication, right? So the communication method is usually TCP/IP. There are other ways, to do it, but that's the common standard. Okay, so you have networking protocol layer, and again, many layers for you to eventually go to the physical devices. All right, so the application is one of the most important things that you need to focus on, okay? Because in the end, operating system is useless if it doesn't support the applications well, right? So the applications are sort of the king of the machine, okay? They are the one that needs to be, that need to be made happy, by the operating system, okay? Because otherwise, so what happens when you have a slow operating system, right? Then your application developer says, well, my users are very unhappy, because my user, when they run on your machine, they said it's too slow. Okay, so there's nothing I can do. I'm a developer for your platform. Your platform is very slow, so I look bad because my user complained to me, so I'm complaining to you, the operating system developer, to say that your operating system is too slow. Okay, if I complain a few times, says, hey, next time I'm going to develop for a different operating system, where that operating system is fast. Okay, so therefore you have to support the application program. You have to support the application users. You also have to support the application programmers. You got to make them all very happy. Okay, otherwise you're out of business. All right. Okay, so from from their view, right? Our system has processes, threads, file system, terminal, network interface, all the stuff we mentioned before. Okay. Now we're going to sort of look at how the application use them and how does that affect the design of the operating system. All right, so the application basically, their abstraction is, their processes, their threads, their files, all these kind of stuff, right? And that's all they, that's all they think that the hardware is. Okay, they don't really know, the actual detail of what's being plugged into your machine. Okay, all right. So the purpose of they having an address is that the address is the purpose of the process, right? What is a process? And I mentioned before, a process is just a data structure. Okay, so process is a collection of data structure that support the concept of an address space. Okay, so the application view, the process as when I run my program, I have an address space that I can do stuff with. Here are the local variable, here are the global variable, here are the program, and stuff like that. I can do malloc, I can push stuff onto the stack, all these kind of stuff. Okay, the process can also say, well, it's going to holding a group of threads together. So the user says, well, I can create multiple threads. They all share the same address space. Okay, and they can, sort of run kind of in parallel. And the more processor I have, potentially I have more parallelism in my processes. Okay, so that's that's what they think. Okay, they also think that there's something that the operating system will provide that can remember the context, the execution context for my threads. Okay, so this way when I run on this machine, I can actually feel like I own the machine. Okay, because whenever the machine needs to switch to run some other thread, eventually it will return to my thread, and my thread will continue to execute as if there's no interruption. Okay, so so my sort of program knows that some kind of a context are being maintained. Okay, if I have opened a file, the file will continue to be opened. If I have read 100 bytes from that particular file, if I continue to read, I will read the next 100 bytes. Okay. Me, as an application programmer, I don't have to remember all the stuff. All right, so that's part of the file system abstraction for the programmer, that there are these contexts that are maintained inside the operating system, so they don't have so the application programmer, they don't have to worry about these things. All right. Okay, so the address space is a set of addresses that threads of the process can usefully reference, right? And we always draw this picture. Okay, if this is the address space, then the thread can access any memory location over here. Okay, if you have a thread want to access the text segment, can it do that? Sure. Access data segment, no problem. Stack, if you have a precise address for any location in the stack, you can read and write to it. Go ahead. Okay, you're free to do that. Okay, somewhere in the heap, you have a memory address, you want to use it, well, you can just go ahead and do it. Okay, what about if you want to access memory location 0? That you can't do it because, that's one of the programming model. If you access read or write memory location 0, you're going to get a segmentation fault. Okay? So there are ways that you're supposed to use the address space. Okay? For example, in the heap, okay, the heap area, the heap actually is not infinite. Okay? There's actually something called the top of the heap. Right? Here's the bottom of the heap. Where's the bottom of the heap? It starts at the end of the BSS segment. Right? BSS is here. Okay? At the end of BSS, that's where the heap starts. So we know where the heap starts. Heap also ends at something called the break. Okay? There's something called the BRK, the break. Break is the top of the heap. Okay? If you want to access the memory location above the break, what's going to happen? Well, you're going to get a segmentation fault. Okay? So that's part of the abstraction of the address space, is that there are these places called the break, and also the stack. The stack has a stack size. If you try to, push stuff onto the stack beyond the size of the stack, you're going to get a stack overflow, right? So there's some additional understanding of how this address space is supposed to work, okay? And that's the abstraction that are provided for the application programmer. All right, so let's talk about some of the, issue about preparing the address space, okay? So how does the operating system initialize the address space region, okay? The simple approach, right, we saw, right, you do, when you do fork, right, you have process, here's the parent process. Okay, when you do a fork, you create a child process, right? Okay, one thing that the operating system can do is when you create a child process, you copy the entire address space to the child process. All right? So if this is 4 gigabytes and this is 4 gigabytes, that's way too slow, right? If you want to copy 4 gigabytes of location, it's going to take you several seconds to do that. Okay, so it's actually very slow. Okay, how do you speed this up? Right. So first, let's look at the text segment. Right, the text segment is right here, right? Okay, when we create the child process, do we have to copy the text segment? No, we can actually share it, right? Okay, if we can share this, okay, then we don't have to copy it. We just have to point to it, right? Okay, so how do we really share that? Well, it turns out that, we can use this picture. Okay, this picture, we just saw it, right? For one program, here are the physical pages for the text segment, right? Main is here, okay? And then subr is here, printf is here. Printf is take up the entire page. Printf, write, startup, they're all here, right? Okay, if we need to create another child process, what do we have to do? Well, we can just point to the same place, then we're done. Okay, so using the page table will actually save us the trouble of copying memory. Okay? So what happens is that when we create a child process, process number 2 over here, every process has their own separate page table. Okay? We just copy the entire page table, just copy it over. We're done. Okay? We don't have to copy the address space at all, as it turns out. We just copy the page table. The page table is much smaller, right? So when I copy the entire page table, this is for the child process, this is for the parent process. And now, when I try to run the main program, what happened? Main is right here in the child, right? this guy will point to this page. Okay? So is the address space there? Yes, it's there, right? So basically, this is kind of like my address space. If I start executing code, then everything's going to work. Okay? So all the code is okay to share then. But as it turns out, well, not everything can be shared, right? The data segment over here, that's going to be a problem, right? If I share it, what's going to happen is that this child process is going to write to one of these memory locations. It's going to be surprised when the parent process says, hey, who changed that memory location? I haven't changed it yet. Okay? So these read-only these read-only pages that can be shared, but the read-write cannot be shared. All right, so how do we deal with this? We're going to continue in the next lecture for this. All right?
This has been CS402 on Monday, June 16th, 2014.